Thus far, we've gotten a lot of intuitive notions of privacy. We've walked through an example of local differential privacy. We've walked through a differencing attack. We've walked through basic queries and the definition of sensitivity. And now we have the basic building blocks to talk about what the true formalized definition of differential privacy actually is. This will also lead us into our first implementation of global differential privacy as well. In particular, we're going to look at global differential privacy and ask the question, how much noise should we add after the query has been run, to sort of noise up the entire query or database with one block of noise. We will find that this global differential privacy will also intuitively relate quite nicely to the formal definition of differential privacy, which we will propose along the way. So what we're going to do here is we're going to create a database with our query and then analyze it with the formal definition of DP. We're going to add noise to the output of our function, and we have two different kinds of noise that we can add, Laplacian noise or Gaussian noise. And in order to know how much noise we should add, we will appeal to the formalized definition of DP. This is the definition proposed by Cynthia Dwork. It's the E equals MC squared of differential privacy. It's the most important formula in the field, and it doesn't create differential privacy necessarily. It's not a method of adding noise, per se. Instead, it's a constraint so that you can analyze a query with noise and know whether or not this query and noise is leaking too much information. In particular, we have two different measures called epsilon and delta, and these compose a threshold for leakage. Now let me unpack this a little bit for you, what this exact inequality is.
So the previous method of adding noise that we just worked with in the last session was called local differential privacy, because we added noise to each data point individually. This is necessary for some situations wherein the data is so sensitive that individuals do not trust that the noise will be added later. However, it comes at a very high cost in terms of accuracy. So if you'll remember back to how we actually constructed the coin flipping example, you will remember that before an individual sort of gave us their answer, when you would query an individual and you would say, hey, are you performing some sort of illicit activity? And before they gave you their true or false value, they would actually flip their coin at that point, right? And so that means that they were adding noise themselves to their individual data point before submitting it to you, right? And it's this local term refers to the fact that they are locally adding noise to the data before it gets sent to you. Now, if you're familiar with the intuitions of, say, dataset anonymization, even though dataset anonymization is a broken technique and you shouldn't use it, it's probably the closest parallel to local differential privacy to the extent that it is augmenting a data points individually with the intent of trying to be able to release them. But again, don't do dataset anonymization. Don't advocate for people to do dataset anonymization because it's a fundamentally broken idea. However, this leads us directly into the other kind or the other class of differentially private algorithms called global differential privacy. Global differential privacy, instead of adding noise to individual data points, applies noise to the output of a function on data points. And the advantage in general, and this is a little bit of a sweeping statement, but the advantage in general is that you can often add a lot less noise and get a much more accurate result if you wait to add the noise until after you've computed a function. And the reason for this is that many functions actually reduce the sensitivity involved. So, for example, here we have a query over a database. So local differential privacy would add noise here, right? And this is what we did in the last session. We were adding a little bit of noise to individual data points for the sake of protecting, when we were simulating the coin flipping example, right? However, global differential privacy would add noise out here to the output of a function. Now, this doesn't have to be just a single function. This could be a big long chain of functions. It could be a sum and then a threshold and then another sum and then multiplication, or any number of functions that we wanted to chain together. And we can add noise in the middle or at the end, wherever we wanted to do this. As a general rule of thumb, as you process data more and more, it is quite common for sensitivity to go down. So a good place to start if you're trying to figure out where you want to add noise in your system or in your pipeline is to sort of lean more towards doing it as late in the chain as possible. because the later you go, the more individuals you have likely aggregated over, the more processing you have done, the more likely you will have done to do thresholds or squishing functions like sigmoids and ReLUs or any of these other kinds of post processing on your data. And the better the chances are that you'll do things that actually reduce the amount of sensitivity and actually end up reducing the amount of noise that you have to add, giving you a more accurate result with less privacy leakage. Okay? So just these are a few general statements that I'm making about global and local differential privacy and why people prefer one over the other. So if the data is so sensitive that people aren't going to give it to you, then people tend to lean more towards local differential privacy because sort of the individual data owners are just sort of so scared that they want to protect their data before they hand it over to what's called a trusted curator, who is the party that is generally referred to as the one who's actually performing differential privacy. And that's the reason that most people who use local DP use local differential privacy, whereas people use global differential privacy when they're more interested in saying, hey, I really need the output of this to be accurate while still having the same level of privacy, right? So if there's a trade-off between sort of how much the data owner is willing to trust the person performing differential privacy here. So if you can facilitate a setup where differential privacy is being performed over a large data set and they can trust that you're performing differential privacy correctly, I would strongly advocate for you to lean towards global differential privacy because it can be a much more accurate method of stripping out private information. Okay, so enough on global and local differential privacy. Both of these lead to the next question of how do we actually measure how much privacy is being leaked inside of a differentially private algorithm. And this leads us to the formal definition of differential privacy. So even though up to this point, for the sake of making it intuitive, I've been giving intuitive explanations and sort of high-level intuitions on how differential privacy works and what it's really all about. Differential privacy itself, the term differential privacy, is actually a very formalized definition. It's actually multiple definitions. There are multiple proposed definitions of differential privacy. The one that we're going to be talking about today is the one that's been proposed by Cynthia Dwork, and it's actually the most well known, the most widely used, and other forms of differential privacy typically build on top of this one, for one purpose or another purpose. So this is a great place to start. And many of the terms and the techniques that we'll be mentioning here are also relevant to other forms of differential privacy. So let's walk through this definition. A randomized algorithm M with domain natural numbers, absolute value of x, so this is basically saying a certain set of natural numbers, is epsilon delta differentially private if for all s in the range of M and for all xy in x such that x minus y is less than or equal to 1. Okay, so let's reread this a bit more intuitively. A randomized algorithm M being a randomized algorithm is this. This would be a globally differentially private randomized algorithm. It's some sort of function on a database with some sort of noise added to it. Now, this noise could have been inside the DB or applied to the DB in here, in which case it would have been locally differentially private. So where the noise is actually added, the exact characteristics of this mechanism is non-specific here. So this could be any function. We don't know what algorithm this is. We just know that it has the ability to query a database, and it is randomized in some way. Okay, so that's what we know about M. Oh yes, and it has an output domain of in X, meaning it could be a histogram over certain entries in a database. So it's discretized in this particular case. And we're saying that this is epsilon delta differentially private if for all the potential things that it could predict, right? So for things S in the range of M, and for all database pairs, so parallel databases such that X minus Y is less than or equal to 1. Actually, these are histograms over parallel databases. So this is saying, okay, a database has a bunch of stuff in it, right? And X counts how many times each thing happened in the database, right? So how many times, if it was a database full of marbles, I don't know, and each entry had a marble of a specific color, right? This might count the number of red marbles and the number of blue marbles and the number of yellow marbles, right? In which case, this would be 3 natural numbers, and the size of x would be 3, and of course they're natural numbers because we're counting individual things. So something to take away. It's discretized. The differential privacy definition is posed in the form of a histogram over a database. Okay, and so we're saying there are 2 histograms, right? And the max distance between these 2 histograms is 1, meaning that they only differ in 1 entry, meaning that they are parallel databases. So they're the databases that formed the histograms are parallel. Okay, so let's just walk through this one more time just to make sure that you understand this sort of setup for this definition. A randomized algorithm M, okay, with a domain in to the x, meaning that they're natural numbers to the x. And actually earlier in this paper, it was identified that this is referring specifically to a histogram over a database, is epsilon delta differentially private if, for all the things that M could predict, so all the potential outputs of M, for all the potential inputs that are parallel databases, right? And this is the part that's saying it's parallel, that this constraint is true. Okay? So the setup is 2 histograms. One is the full database. One is database with 1 entry missing. And this constraint is true. So what is this constraint? Let's start with what we know. M to the x is actually taking our mechanism and running it over this histogram. Okay? My is doing the same thing over every parallel database, right? So it's every database, well, any database, we'll say any database, any database with 1 entry missing, right? So this threshold has to be true for all databases, but it's only actually expressing 1 at a time, right? But we're saying that it's true for all databases. And so, okay, so we got the query over the parallel database, we got a query over the full database, right? And it's returning something in S, okay? So S is one of the possible things that it could be predicting, one of the things in the range M, all right? Now, we're saying that this is true for all things, but you can think about it intuitively in your head as, for predicting the red marble, right? So what is the distance between the distribution over all the things in the database, the probability distribution over all things in the database, versus the probability distribution over all the things in the database minus 1 entry? Okay, so random distribution over things in the database, objects in the database, random distribution over objects in the database with 1 entry missing. Okay, and now the question that we want to ask, the question that is the core focus of differential privacy is, how different are these 2 distributions, right? How different is the output of my mechanism, the prediction of my mechanism, when I remove an entry from the database? How much does it change from here to here? And the measurement of the maximum amount that these 2 distributions are different is measured by 2 parameters, epsilon and delta. E to the power of epsilon constrains how different these distributions are. Okay, so it's sort of the primary constraint, we might say. And some algorithms actually only use epsilon. So here we say, if epsilon was 0, then these distributions are identical. We're going to ignore delta for a second, right? So if epsilon is 0, then e to the epsilon is 1. And these distributions are identical, right? So this less than or equal to would be equal to. Now, so epsilon 0 we would say is perfect privacy. Epsilon 0, delta 0 would be perfect privacy. So if this constraint was satisfied at epsilon 0, delta 0, then we have no privacy leakage with M on X, right? So by computing the output of this randomized mechanism. However, let's say epsilon was 1. Okay, well that allows some privacy leakage. Exactly how much that is, we can get to that in a minute. But something that is very important to take away is that something can satisfy differential privacy, can satisfy this constraint but still leak private information, right? So leaking or not leaking it's not a all or nothing kind of thing. You can actually leak small amounts of statistical information. Now, delta is the probability, which is usually very small, the probability that you will accidentally leak more information than epsilon claims that you will leak. So delta is often 0.00001 or something like that, or it's zero. Like it's usually a very, very small probability when it's non-zero, and it's basically saying, hey, most of the time you're going to be able to keep everything underneath this amount of leakage. These distributions are going to be, very, very, they're going to be at least this close most of the time, but only this probability will they actually not be. And this is basically saying that, if your queries for just the right thing with just the right random noise, some probability you will accidentally leak more information. Okay? So this is the constraint of differential privacy. And so as you might imagine, a tremendous amount of effort goes into developing really good random algorithms such that this can be satisfied in a way that is useful, right? So where we get the most accurate output of our queries possible with the lowest epsilon and delta possible, right? And there are also improvements or modifications to this algorithm, or this constraint that seek to modify it in various ways, which you can observe further in the literature and will lead to some pointers to at the end of the course. So, things to note about this setup. So first and foremost, this is looking at one query. Okay, so this is one query against the database. If you have multiple queries, this is not what this is supporting, right? So multiple queries would have to sort of build on this, and we can talk about how that actually happens in a minute. All right, so this is, but the sort of epsilon delta budget, which is also sometimes referred to as your privacy budget, is satisfied for one query using this particular constraint. Okay, so in the next video, we're actually going to look at how to actually add noise for global differential privacy. So we can say, okay, given that we want to be able to satisfy this constraint for a particular query against a database, how much noise should we add to make sure that we don't spend more than a certain level of epsilon?
So don't move on from this video and rewatch it if you have to, until you get an intuitive sense for what epsilon and delta are all about, because they're crucially important to differential privacy and to the next project that we're going to tackle.